Kia ora. My name is Bill Trompetter, and this is the second presentation about a paper that I've written entitled The Electromagnetic Angular Momentum of an Orbiting Charge. And this presentation is about the maths behind that is used in this in the paper, and I'm going to outline that in this presentation here. So it's the same story, but from a maths point of view. So in the first presentation, I outlined the precession interactions from the literature, outlining the Larmor energy, the Thomas precession, and the electric dipole interactions as based on a point particle. And that when we consider the extended electromagnetic mass of an electron in orbital motion, then for the Thomas and electric dipole interactions, these were based in the lab frame, and in the lab frame the electric fields are radial and straight. So when we integrate the electromagnetic mass for the particles in those, the electron in that frame of reference, they integrate into that of a point particle. So the expressions, those interactions are equivalent to a point particle interaction. However, when we consider the spin-orbit interaction, which is based in the electron's frame of reference, the electron frame's rotating frame of reference, then the electric fields are radial. Are no longer radial. They take on curved trajectories, and we have ended up with a different interaction. And that's what I want to go through here is how do we do that calculation, or how did I do that calculation in the paper? So the way it's done is we want to consider what the spin vector and the precession vector at different radii as it extends out from the charge, and we want to integrate those over all space to end up with the Larmor energy interaction for an extended electromagnetic particle. And as I've already intimated, that in the lab frame of reference, the electric fields are radial and straight. In the rotating frame of reference, the electric fields take on a curved trajectory, and indeed they extend. The electric fields take on a circular trajectory, and they extend as far as a certain radius, and that radius is where the tangential velocity approaches the speed of light, and the maximum radius is given by the speed of light divided by the angular velocity. So the spin elements that we need to incorporate in our equation, we know that the magnitude of the spin is half that of the angular spin. So therefore, the spin elements is given by half times the mass element, or the electromagnetic mass element, times the angular velocity, times the radius squared, and times the angle, or the direction of the spin vector at the various radiuses, times the volume element. So that is the spin element that we need to consider. The precession element is given by this expression here, and we see that it is proportional to the velocity squared. And the additional thing that we have here is that we are not going to assume a G factor of 2, which was an artifact of, which was added into quantum theory to make it consistent with experimental results. We are just going to set it to 1, i.e. we're not going to include a G factor. in our expressions. So when we add the spin element and the precession element, we end up with this expression. And in this expression, we have an electromagnetic mass, which is given by the line 3 here. And that uses an electric field. The electric field is given, uses the rotational, or the radius as seen in the rotational frame, and that is the radius in the rotating frame is given by gamma times the radius in the lab frame. So and so that's given there. To determine the spin direction element, we basically take the angular velocity, the angle as seen in the rotating frame, and that angle is given by the velocity here, the tangential velocity divided by the speed of light. So that gives us this angular, an expression for this angle, and when we take the cos of that angle, we end up with the square root of 1 minus beta squared. And then we also include the angular element here in the rotating frame divided by the angular element in the lab frame, and that we end up with another factor of 1 over gamma. And so the spin element in the rotating frame is given by the spin element in the lab frame divided by gamma squared. And then our volume element is given by the usual expression for in spherical coordinates. The radius which we use is in the rotating plane, and the rotational plane is basically the radius of gyration that we need to consider. And so our expression, when we need to integrate over the different variables, i.e. the radius, we need to integrate over phi, which is in the rotational frame, and in the plane of rotation. And we also need to consider theta, which is in the directions away from the rotational plane. And so we also need to consider mass elements which are not directly in the rotational plane. And so we need to incorporate, we do that by using sine theta. So we can incorporate the distance from the charge of mass elements which are not in the rotating frame by using sine theta as shown in this expression. And we can also change our integration limit using the same expression. So this allows us to convert an arbitrary radius r dash to the radius in the rotational plane using these expressions here. So that's what I've done in this expression. And then separating out the integrations over the 3 different variables to do them separately. The last one here is straightforward. as is the 1 over theta. Now this one here, we can simplify that by just changing the variables. So the radius, the perpendicular radius over the maximum radius, if we assign that to x, then we can change this integration to this form here, and this readily integrates to 128 over 3,465 times the maximum radius. And we can convert that to that fraction to this form here, and that can so our total expression now comes out to be this term here. Now you can see that this term is proportional to 1 over the maximum radius, and we can, what we really want is to turn that into the orbital radius, an expression for the orbital radius. And so we can do that by simply, instead of 1 over r, this is line 8 here I'm pointing at, 1 over r is the same as 1 over the orbital radius times the orbital radius over the maximum radius, which is the same as 1 over r times beta. And so that's what I'm doing in this this final term. I'm changing it to this form here. So we end up with k e squared over 2r times beta over 137 times 137.87. And this is the expression that I derived in the paper. I managed to do one further refinement to this expression by incorporating a relativistic aberration. So that is where we consider the relativistic transformation of angles in a moving frame. And so when angles are, when an object is moving, then it will observe a different angle to one compared to when it's at rest. And that is done using the relativistic aberration formula, which is given here in the top line. So, and what we're doing is the electron is moving with a certain velocity. It should be v naught here, so that we end up with, so this is the relativistic transformation of an angle given by this equation. And so the elements which we are now considering or including because of relativistic aberration are given in red. So therefore our expression transforms to this. Again, I'm including the new elements because of relativistic aberration here in red. And so we have to integrate, so this becomes our new integral, which we have to evaluate. Again, we can transform that integral by using beta naught, by assigning beta naught to 1 over 137.87. We incorporate that into our expression. And so that transforms, again, that transforms our integral to become this term. And so you can see here that our expression for the Larmor energy transforms to this equation here. So that's it's an improvement on our previous expression. And so then I took that expression for the Larmor energy interaction term I combined that with the Thomas precession, which transforms it to the lab frame to get this red term, this expression here in red. And then we can compare that with the electric dipole expression given here in blue. And we can see that these terms, which have to agree because they're in the same equivalent expressions for the lab frame energy, only agree when at at a certain velocity, and that where that velocity is beta equals 136 over 0.97. And so that means that that's the only point at which the orbital velocity is agreeable between the frames. And so that defines the fine structure constant to be this value, and it is as determined. This value is 99.95% of the experimentally determined value, and furthermore, it's effectively deriving an expression for Planck's constant as well, because Planck's constant and the fine structure constant are very much related, as shown here. And the difference is very small compared to the experimentally determined value, but we've only used first order theory here in this paper. And all I've really wanted to do is to show that this approach is a viable approach to show that we can do this, that the theory is valid, and that more work, further second order and third order effects can be incorporated and to achieve an even closer agreement. As I've mentioned, we did not assume a value for the G factor. We just set it to 1, or basically didn't include it. The G factor of 2 was not needed, and that our theory here, based on classical electromagnetism, correctly describes the spin angular momentum. Furthermore, the fact that we did not set use a G factor, or G factor of its value is 1, means that our precessional frequency for the Larmor precession and that the Thomas precession are equal and opposite, which means that there is no net precession in the lab frame. And this makes sense because in the lab frame, we observe an electric dipole and an electric field, and if they're not aligned, then the torque will act to align them, will not act to generate a precession. So this makes good sense. And so in summary, these results reveal the surprising result that the fine structure constant and Planck's constant are a natural extension of classical electromagnetism, and that quantization of angular momentum is a consequence of the expressions that we've derived agreeing, and that basically that energy is conserved between frames for the electrons in orbit with synchronous rotation. So that's it. Yeah, I look forward to where this might go. Okay, thank you.